So in this video, I'll be discussing the Dieckmann condensation reaction, which is pretty much an intermolecular version of the Claisen condensation reaction. This reaction was founded by none other than Mr. Walter Dieckmann, who was a German chemist that studied at the University of Munich in Germany. This reaction is performed with esters and works to produce 5 or 6 membered rings. So we'll go ahead and take a look at the reaction. So a 1,7-diester starting material results in a 6-membered cyclic beta-keto ester. So with that, a 1,6-diester starting material results in a 5-membered cyclic beta-keto ester. And we'll get more into that with these mechanisms. So to start, we're starting with the 1,7-diester starting material. You got your 2 esters here on the sides. And so as you can see, this structure is pretty symmetrical. And so with that, we're going to start with our ethoxide. Which is going to pull that alpha hydrogen off. This being a strong base, this is what ethoxide looks like for you guys. So I'll change the color over. So these lone pairs from this oxygen are going to move over and attack that hydrogen. And then, so from there, this is what you'll have. Oops. So here you'll have a negatively charged carbon, which will then attack the carbonyl carbon here. Let me do that in a different color. We'll attack that carbon there, which then kicks there. So from this step, making that connection, this is where our 6-membered ring comes from. So just to go ahead and number these and put this in perspective, we're going to start counting on our negatively charged carbon. All right, 5, 6. And then for our 6-membered ring, this is what we're going to get. So off of your carbon number 1, you're going to have your ester group. And whereas on carbon number 6, you will now have a negatively charged oxygen. And then, of course, your ethoxide ion there. So with the lone pairs here on that oxygen, these lone pairs are going to be used by oxygen to kick out that ethoxide ion. So show our pushing arrows, which will then bring you to this structure here, with a double bond to oxygen there, and then of course your ester group there. So remember that we do still have our hydrogen here. So in order to get rid of that, we're going to have to deprotonate this eventually. But for now, we're going to move with another ethoxide, which will pull and remove lone pairs from this oxygen, or remove this H, which then leaves that carbon negatively charged. Okay, so like I said, that carbon is negatively charged. And from there, this isn't too stable, so we're going to make it stable by acidifying it using HCl, which we commonly use in the lab. So of course, that negatively charged carbon picks up that hydrogen. To acidify, in which this is what we are left with. For time purposes, I've already got this one all drawn out, but I will discuss it with you guys. So this is with our 1,6-diester, where we create a 5-membered ring, which I'll explain why. But here we see that this structure isn't symmetrical, unlike our last structure. So here we can choose, between these two hydrogens, which one we want to remove. So, this one I have worked out for hydrogen B. So basically our ethoxide here is going to attack that hydrogen and remove it, which then gives us this structure with the negatively charged carbon there, which then attacks the carbonyl group. And whereas I numbered these so where nothing gets lost while creating the ring. So starting at the negatively charged carbon there, we got 1, 2, 3, 4, 5. Seeing as till we create a 5-membered ring. So off of our 1, we can see that we have our ester group there. And then we have our ethoxide group as well as a negatively charged oxygen there, as well as the methyl group that we have coming off of our 2 carbon here. So the lone pair of electrons on this negatively charged oxygen wants to reform that pi bond, which expels the ethoxide group, which leaves you with this structure here. So this structure here, we still have this hydrogen present, with it being a basic solution. So in order to remove that hydrogen, our ethoxide kicks that hydrogen, or attaches to that hydrogen, grabs that, which removes that alpha hydrogen. So now we've got this carbon that is negatively charged, which is our 1 carbon. And so we're going to acidify here with HCl, which we've seen numerous times. But that carbon there is going to go hit that H, and then now we come to our final product here, where everything's balanced, everything's happy. If we were to work this out with hydrogen A, then this is what we would get on this side. So these were the sources used in finding the information for this video, and I hope you guys enjoyed it, and thanks for watching.